Hello everyone, my name is Aditya Shenoy from Brainy. This video is the second part of the Fibonacci numbers dynamic programming version that we have started in the last video. In this video, we are going to see the tabulation version of the dynamic programming. In the last video, we have seen the working of the memoization version of the dynamic programming, where we left the video last. Before going into the details of the tabulation, let's see the recursion tree over here again. In the top-down approach, for calculating the results of the root node, it calls its child nodes. It calculates the value of its child nodes using recursion, and this recursion goes on until the values of the leaf nodes have been calculated. Then these leaf node values are returned to the parent node, and this process goes on until the results are reached to the root node, and the final value of this node will be returned. In the bottom-up approach, the calculation of the results start at the leaf node, and these results are added similar to the case of the recursion, and these results are accumulated again to the root node. The top-down version is memoization, and the bottom-up approach is tabulation method. So which method is better over here? Well, this answer depends totally on the problem that we are solving in our hand. For example, let's consider we need to search something in this tree and say that the result is over here. When we start the searching process, we will start over here in the top-down approach. It will call its recursion calls, and once it finds its result, the calculation ends without needing to call the child nodes over here. That means that in some problems, the whole recursion tree is not being traversed. This is the ideal case for the memoization version. But in our case, for calculating any Fibonacci number, we need to know the values of the Fibonacci number of each of the nodes. Although we have eliminated the overlapping of subproblems by memoization, we still are finding each of the nodes at least once. That is, even if we are removing the duplicate calculation of Fibo 2 over here, we are still calculating it once. And that means the whole recursion tree is being traversed. Thus, this problem is suitable for tabulation method. Let's see the working of the tabulation method. The memoization version contains recursion. Contrastingly, the tabulation method of dynamic programming contains loops instead of recursion calls. Hence, we will remove this. Like the memoization version, we will still check if the value of n falls in any of the trivial cases. That is, if n is in the list of 0 and 1, we will return n. This line is exactly the same like the previous code. That is, if the input is one of the two values 0 and 1, the output matches the input. For recursion cases, the case over here changes, the code over here changes. We will start with the DP data structure, that is a list over here instead of a dictionary, and we will store the output of the trivial cases. That is, for n equal to 0 and n equal to 1, the values were 0 and 1. We will initially store these results in a list. Then we will start a for loop that will start that will have a value of 2 initially. Why 2? Because we have already calculated the 0th Fibonacci number and the first Fibonacci number, and we need to start calculating the Fibonacci numbers from second number onwards, and we will end this for loop at n plus 1. Remember, this range function does not include this number. Hence, this range function will end at n plus 1 minus 1, that is at n, and that is exactly what we want. So, like this recursion case, we will still add dp I minus 1 and dp I minus 2. That is, for calculating second value, we will find the value of I minus 1, that is the value preceding it, and I minus 2, that is two values behind it. But as you can see that for each value, we cannot store it simply in the list because there is no second element over here. That is, this list contains only two elements, 0th element and the first element. There is no second element to assign values to it. Hence, to overcome this problem, instead of assigning, we will append this result to the list. So the values of second last element and the last element will be added, and it will be appended at the end of this DP data structure. And one more change we can do here, that is, whatever value we are calculating over here, we are calculating the last element of the list, we are adding the last element of the list and the second last element of the list. Hence, we don't need to write this I minus 1. Instead, we can write just minus 1 and minus 2 over here. Whenever we see a negative index in a list, that means that it is indicating first element from last, that is the last element. Similarly, this indicates the second element from last, that is second last element. We will see the exact working of this code by visualizing the state of the DP data structure once we finish this code. And this loop will keep on appending the results at the end of the list until we reach the end of the loop. At that point, we will have the complete Fibonacci number sequence stored in this list, and hence we can just return the nth value in this DP data structure, which will contain the nth Fibonacci number. Let's see the working of this code. We are again passing n equal to 3 over here for illustration. It will check if value of n equal to 3 falls in any of the trivial cases 0 and 1. It does not, and hence this condition becomes false over here. It will skip the next line and it will initialize a DP data structure having values 0 and 1. Initially, the I will take the value of 2, and over here we can see that dp minus 1, that is the last element of the dp data structure, is 1, and the second last element over here is 0. That is, the second Fibonacci number is the addition of last element and the second last element of this dp data structure. Hence, these two numbers, the second last number and the last number, will be added, and this result will be appended at the end of this list, as you can see over here. Now I will take the value of 3. Notice that n's value was 3, and so n plus 1 will be 4. But this range function does not include the value of 4, so this loop will take values from 2, 3, and it will not include 4. And hence this is the last iteration over here. I equal to 3. Like the previous case, it will add the last element and the second last element. Now as the DP data structure has changed, the last element is now 1 and the second last element is now 1. And hence these two values will be added to get the value of 2, and it will be appended again in the DP data structure. Once this loop ends, we will find the third index, that is 0, 1, 2 and third index of this DP data structure, and we will return this value. So this is the working of the tabulation version. It does not include any recursion, and hence it is slightly memory efficient, but at the same time it is storing the results like memoization, and in some cases we don't need to store the entire results of the recursion tree. There are some problems in which memoization works better. If you guys want to see such examples where memoization version works better, please let me know in the comment section if you want to see such examples. Now we can do something better over here. If you guys have noticed that for calculating any Fibonacci number, we just need to store the last Fibonacci number and the second last Fibonacci number. We don't need to store the previous Fibonacci numbers. And hence we can use this to optimize this code to be space efficient. For example, when we are calculating the second Fibonacci over here, we were adding the last element and the second last element over here. And for calculating the third Fibonacci number, we were calculating the second last number and the last number again, but we were not using the values that were present before the second last element. And hence we can keep on deleting these values when we don't need that, when we don't need those values again. And so we can add just one line here, that is, once we append this result, we will delete the first element that is present over in the list. And one more change we need to do, as we are deleting elements from the list, there will be no nth element present in the list, and hence logically the final value that we want will be at the end of this DP data structure. And hence instead of returning DP of n, we will return DP minus 1 over here. So by adding just one line and modifying slightly this line, we have optimized this tabulation method to be space efficient. Let's see the working of this space optimization and how it actually optimizes the space by visualizing the code. As you can see that this is the code over here. We are passing n equal to 3 again. It will again check if n falls in the base case. It does not, and hence this condition becomes false. It will again generate the DP data structure as before, containing the values of 0 and 1. The for loop will start with the value of I equal to 2. For this step, it will calculate the sum of the last element and the second last element, that is 1 and 0. It will add those two numbers and it will append the the sum to the end of the list. That is 1 plus 0 is 1 is being appended at the end of the list. But now, as we don't need this value anymore for future calculations, we will delete this value. That is, we will delete the first element of the list. As you can see, that the value of 0 was deleted from the DP data structure. Now the I will take value of 3. We will add the last element and the second last element, that is 2, and we will append this result again at the end of the DP data structure. We will delete the first element, that was 1 over here. This is the end of the for loop, and we will return the last element. If we didn't change this from dp of n to dp of minus 1, we will have an error over here, because there was no third element over here, because we were deleting the first elements, and hence the list is shrinking over here. And logically, we just need to return the last value, because that is where our for loop ends, and hence we will return the last element, that is 2, to the probe as the final result of our program. So yeah, this was the space optimized version of the tabulation method. If you end up liking this video, please give this video a like. Comment any feedbacks that you have for this video or this channel. You can also comment future topics that you want me to do in this channel, like some data structures, algorithms, some console applications, some games, or anything else that you want me to do. Subscribe to see more such videos, more such illustrated descriptions of the algorithms, and I will see you in the next video. Take care. Bye.